There we go. Okay.
Amazing.
So we're going to discuss what exactly is content addressable memory. Then we're going to talk about the structure of Hopfield networks and how they work, what the limitations are, and then a brief conclusion. So you go to the next slide. All right. So in a computer, there are essentially two ways of saving information. You can save it with random access memory, which is based on the location where it's stored, and then to retrieve the memories, you have to know the exact location where it is. Whereas with content addressable memory, it's information that is saved by the content, and you can actually search it up and retrieve the original memories with partial matches. And for instance, Hopfield networks can be used to retrieve the original pictures from noisy or otherwise corrupted versions of them. And this is somewhat analogous to how the human brain stores memories. You can think of how if you're shown a blurry photograph of someone you know or a place you've been before, then that can instantly trigger memories of it. So if Simon wants to talk about the structure now, I'll hand it over to him.
Yeah. Okay. So a Hopfield network is mostly used for images which have pixels, which can be seen as neurons. They can be on or off. In this case, they have a value of +1 or -1. These are used in this weight matrix equation, where the vector is multiplied with its transposed version, an identity matrix is subtracted, and for every image that you want to train into the network, you sum all of these matrices up with one another. So now, if you have a picture made into a vector and the vector is kind of noisy or the data is kind of corrupted, you can either synchronously multiply with the entire weight matrix a bunch of times, and then you will get your original image back. Or you can fire the vector with random columns in the matrix to slowly get your picture all back. And what the network is essentially doing is it is trying to lower the energy function of the entire network. So for a live demonstration, here is the code. If I run it once, then we can see here an energy graph, the initial image that we trained within the network, and the initial image that is corrupted with noise. And this network was trained with about 4 images. I can give a noisy image of any one of these 4 images, and it will return the correct image back. And here is a nice result for the asynchronous way in which the network tries to reduce its energy. We start with a noisy image, and then slowly we get our image of a house back. And now Zach is going to talk about the memory limits.
Yes. So unfortunately, you cannot store an infinite number of images in this network. There is a limit to the number of memories that can be retrieved. And this limit is equal to about 18% of the number of neurons, or the number of pixels in the images you're using. And this is calculated by setting the probability of having a single bit accidentally flipped at 1%. So if you have more memories than the 18%, your error rate will be higher than that. However, if you're not careful with the types of images you store, you can still get spurious results due to too much overlap. So you can see an example here where an initial image that's clearly supposed to be a 5 was accidentally turned into just random garbage. This is because this network was trained on just the numbers 1 through 5, and all of the digits had too much overlap. They all had like horizontal parts at the top and bottom and large empty portions on the left and right. And all this overlap caused it to output a spurious image that the network was never trained on. And the main way to combat that is just to be more careful with the images you store and make sure they don't have as much overlap. Yeah, so in conclusion, Hopfield networks are a pretty easy, simple implementation of content addressable memory that can retrieve images from noisy or corrupted versions. However, they do have a lot of limitations with the number of memories that can be stored, and also with spurious results if there's too much overlap. And Hopfield networks were a very good starting place, but there have been some better techniques that have been developed in the years since they were designed.
Excellent,
So now,
excellent point you left it over with your, sorry, I jumped in. You want to say something else?
yeah, no, I was just gonna say that now we can take a couple questions.
Yeah, so you've left a perfectly dangling spot. So since you seem already to know a little bit about that, what can you do to have more memory stored in recurrent neural networks such as the Hopfield?
One of the things that we did, which worked immediately, was to make all of the numbers much thicker, because a lot of the numbers that we created had a lot of empty space on the left and on the right, and they had a lot of overlapping dark pixels on the top, middle, and bottom. So if you just use more space, you already get more varied images. A lot of articles also talk about orthogonal images, which is basically that you want just as much variety in your pixels as possible.
Yeah, it's the XOR problem in the context of Hopfield networks. Here, you're saying that you want to balance your pixels in dark and bright. In fact, the memory capacity that you've stated, 0.18 for neuron, is under the assumption that the figures that you're wanting to store are completely uncorrelated.
Yeah.
When you increase the thickness of a representation of a number, in fact, you're correlating some neurons. And that will actually increase your memory capacity, all things considered. So this is what you found out. Lovely.